Hello everyone, welcome to our March webinar. Today I'm going to present to you how to perform proper cleanroom classification. If you already attended our previous webinars, we have been discussing about the same issue with a different aspect. In general, we talked about the GMP requirements and also ISO requirements. Now we are going to see how we will be implementing them in field and what kind of data we need to collect and what are the critical processes that we need to control throughout the session. So I'm going to start with a couple of explanations for you. First of all, we have a questions in chat box, depending on where you are logged in. If you are using a web browser, then you are going to see this chat box. And if you are logged in through the GoToWebinar platform screen, then you are going to see the questions session. Feel free to type in any questions into these parts. And also I have these handouts ready for you, and also our portable particle counter Apex Z information in PDF file. So let's start with a couple of items. First of all, my name is Hashim Solmaz, and I'm the General Manager of Lighthouse Worldwide Solutions, EMEA Operations. I'm also serving as a head of delegates in ISO TC209, which is responsible to write cleanroom standards in general. Today we will be discussing about -1, and this is also part of ISO TC209's responsibility. And I also served as an expert in ISO TC209 Working Group 3 cleanroom test methods. And I am a chair of Cleanroom Technology Society of Turkey and the different responsibilities in ICCS, International Confederation of Contamination Control Societies. And I'm also a faculty of IEST Contamination Control Institute. So this webinar content will be about the cleanroom basics first, to understand in general, and the definitions about -1, the latest version in 2015, and the general definitions again from GMP, the current version which was published in 2008, and the draft version from 2020, how to collect the data and how to reach to the cleanroom environment and how to collect this information from the field, an application example that I'm going to share with you today. Classification report also will be part of this presentation, how to prepare your report after collecting all this raw data, what are the pass and fail criteria for this expectation, interpretation of your results, how you will be using this information. In general, people are very good at collecting this information, but when it comes to making a trending or pass and fail criteria, then we have a little bit issues, so we want to cover this part. And what will be the period and for requalification of your cleanrooms and classification. And for some of your questions, I'm going to answer throughout this session. Let's start with cleanroom classification. Imagine you have a very specific day with your family and you're all having your nice suite. I was wearing my shirt before, now I have my special Lighthouse shirt with me, and I'm ready for you because I already know that I'm going to have the webinar today. This is what we call a classification progress in cleanrooms. You already know that somebody will enter your cleanroom either from your personal or a third-party company and will certify your cleanroom. That's why you tidy up everything, clean up all the surfaces, and make sure that HVAC system is up and running properly. And you are already know that the last 1 hour, 2 hours whatsoever will be a specific definition for your next 6 to 12 months. That's why I always consider this classification as a nice family portrait. What about the monitoring? You should expect anything. You can be in anywhere while someone is just taking your picture, which you are not happy with. In a social media, most of the time people are posting your picture and you don't like it because you're not expecting them to take a picture at the moment while you are eating or playing anything and getting ready for the picture, but they were so fast and moved faster than you, then you're not happy with the picture. This is what we call cleanroom monitoring. Anytime you should expect this picture while you're in production, while you're in preparation of your cleanroom, or the system design, from the system design phase all the way to the production. So you should be ready for any kind of glitches that you will be facing. That's why the monitoring is the toughest part. But today We will just discuss about the nice part with our suites, and so we will move on with the cleanroom classification. A couple of basics. One of them is occupancy states. We have three phases. One, first of all, is the as-built conditions. As-built is what you order to your cleanroom manufacturing company. Just the conditions where the complete service is in field, no equipment, no furnitures, no materials, just the walls, ceiling, and the floor itself, along with the HEPA system in place, up and running. So this is what you expect from your cleanroom manufacturing company. Another one is at rest. If you put all the equipments into the site without any personnel inside, but all these equipments are running. Running doesn't mean they're in a production phase, but for example, if we are talking about the pharmaceutical companies, then these companies will be running their machines, all the belts and everything will be up and running, but the production not in place. Idea behind is to expect what will be the total contamination that will be introduced by your machinery system to your cleanroom environment. That's why in at rest condition, we want to see this part without any personnel. So if you consider without any personnel expectation, of course, if your personnel will leave the particle counter inside the room, in order to make it at rest, you should use these delay mode, and your operator will move out of the area, and the particle counter will stay in a delay mode a couple of minutes, then will run in at rest conditions. Operational conditions, you need to have the same at rest conditions with the specified number of personnel present, not less, not more, just an enough amount of people who are making a proper work inside the cleanroom. Reason I explained in detail, because sometimes in order to keep it in operational, even they are having 4 or 5 personnel at the same time in a cleanroom, during testing they're just letting one to go in. If you are working with 4 or 5 people, keep it as it is. So don't expect to have more people in the clean room just to see the worst case scenario, because we don't want to see that. We just want to see how many people are doing this operation, and while they are in operational mode, limits are within the specs. So a couple of definitions that are made by 2015 version of ISO 14644-1. One of them is routine cleanroom particle counting for classification, and the risk-based approach, typically on an annual basis. This is what the standard says. Certain number of sample locations to be defined, and certain volume of air to be sampled at each locations, and it will be equal for each and every location. If all locations sample averages passes, cleanroom passes. If you are failing in one zone, this means your cleanroom will fail too. In GMP Annex 1, 2008 perspective, you will expect the same calculations, just the limits are different, because in 2015 version, especially for ISO class 5, we have been using 0.5 and 5 micron anymore. Just 0.5 micron is available, but 5 micron is not available in ISO class 5 table anymore. That's why GMP has its own expectations in terms of 5 micron. We will talk later on, but keep in mind, 5 micron is the most critical parameters, especially for the monitoring and also for the classification in pharma. Even ISO is not expecting you. Even in a long run, GMP says, I don't want to see 5 microns in classification. I will recommend you to keep counting these 5 microns for yourself only, because this is a nice early indication of any failure in your cleaner. So you don't want to miss this opportunity to see this information. That's why keep counting 5 microns. So it's in general, we have the same definitions which are described by the ISO 14644-1. Only addition, for classification of grade A zones, you need to sample at least 1 cubic meter of air in each sample location. That's an addition from the ISO perspective. 2008 version of ISO Annex 1, sorry, GMP Annex 1, is giving you A, B, C, and D as at rest and in operation table. We all know that. In ISO conditions, we are not considering at rest and in operation. In fact, you might expect to have a different ISO classes for different occupancy states of your cleaner. For example, you can say in at rest, I'm going to classify this room as ISO class 7. but in operation it will be ISO class 5. Vice versa, I make the comment in the wrong way. In at-rest conditions, you should expect it to have ISO class 5 to be parallel to GMP, but in operation conditions, maybe you will expect it ISO class 7. So this differentiation is not through the classification number, it comes from the definition that you made. So the GMP perspective, if you consider grade A, B, C, and D with at-rest and in operation according to ISO, you will see 4.8 for grade A because the limit is not 29 but 20. So the previous version of ISO was giving you the decimal cleanroom classes. In fact, this is also removed from the ISO standard. So we're not having any ISO class 4.8 anymore. We will consider it as a specific requirement from the GMP side. 2020 draft of GMP Annex 1. For cleanroom classification, the airborne particles equal to or greater than 0.5 and 5 microns should be measured. That's one expectation from the standard regulation itself. The grade A zones and the grade B at rest classification should be include measurement of particles equal to larger than 0.5. However, measurement using a second larger particle size, example 1 micron in accordance with ISO 14644 may be considered. So again, if I were you, I would keep watching my 5 microns even for classification conditions. Again, in the draft Annex 1, the table given as this, since it is talking about 1 micron for A and B, I would like to see this table including these 1 micron particle sizes as given in the second example. So here, this one, the 1 micron, I just add this into the table. The original is on the upside in the draft, but I will recommend you to have on your table, have these 1 microns so that the table will also represent the numbers and expectations from the field. Again, number of sample locations and positioning will be through the ISO 14644-1. And the sample locations should also consider all critical processing for the production, including point of fill, stopper bowls, all other critical points. I have an example for this, which I will share today. So we will be seeing the monitoring expectations are also supporting our classification in terms of risk assessment. So for data collection, I have been giving these example as what we need to collect from field, how we will calculate or check from the tables, and how we will pursue this information throughout the process. Data collection, we already know the room area in meters square and targeted ISO class 5, 6, 7, and particle counter flow rate as liter per minute. And what will be the targeted particle size? 0.5, 1, or 0.55, whatever required based on your ISO and GMP ISO or GMP expectations. Data from the tables in 2015 version. Luckily, we have 2 tables which are normative now, used to be an informative for classification limits, and used to be a calculation for the number of particles that we need to, number of locations that we need to consider. Now we have table A1, number of sample locations given, and table 1, normative, which is the particle concentration limits for targeted ISO class N, equal and larger to. So this is table 1. Keep in mind, when we say ISO class 5, 0.5 micron, 3520, this doesn't mean a number of particles as a size of 0.5 micron. This is 0.5 micron, equal and larger to. So when you consider 832 1 micron particles, that's already included in these 3520 particles. That's why the table given the size equal and larger to the considered parameter. Table A1 is the sample locations related to cleanroom area. It's given up to 1000. The calculation is a geometric calculation, starting from 2 square meter area up to 1000. One thing we need to consider, if we are saying 28 meter square area, we already know that 7 locations, but if it's 29, we will move to the larger classification area. No matter if it's 28.1 meters square area, we will move into 32 in this example, or instead of taking 7, you can move into 8. Also, for the limit calculations, if let's say you have a square clean room, but that's 28 meters square area, so you have 7 locations, you can make it 8 in order to take a better shaped clean zones in your clean room. So you are free to add more locations. This is the minimum number of sampling locations given in this table A1. Only calculation from the equation is now data collections, required single sample volume, which is Vs. That's 20 divided by your limit, particle limit, multiplied by 1000. That's still same, not changed. And the minimum required sample volume is 2 liters in any specific location, or minimum 1 minute of sampling to your specific particle counter. What does it mean? What is the expectation? It should be at least 2 liters or at least 1 minute sampling. Forget about this 2 liters because all the commercial particle counters are starting from 2.83 liters, 0.1 CFM, all the way to the 100 liters, depending on the manufacturer. This could be 1 CFM, 28.3 liters. This could be 50, 75, or 100. So you don't have to worry about sampling less than 2 liters. Just worry about collecting these minimum sample time of 1 minute. For example, if your location requires 5 liters, if your particle counter is 50 liters per second, you cannot take 6 seconds of a sample. You should take all the way these 50 liters. Even if it's 28.3 liters, 1 CFM unit, you should still go with the 1 minute sampling. That's the expectations. And each single sample volume at each sampling location shall be the same. So if the expectation is 24 liters, if you're taking 28 from every location, it should be the steady and the same. Prepare your VS table based on your particle counter. What does it mean? Standard is not giving you the VS table. It's still asking you to make your own calculation, but this is what you should expect as a minimum liters to be sampled in each location without defining your particle counter flow rate. I have another examples coming up, which is showing you the number of samples to be, number of locations to be sampled, and also the liters you should expect from your particle counter. This is just an VS for targeted size. If you are, let's say, ISO class 5, if you will be sampling 0.5 and 1 micron, the larger requirement is 24 liters. So you should expect to collect 24 liters in each and every clean zone that you described. But if you are using 1 CFM particle counter, how many minutes you are going to collect these samples is based on this information. As you can see, there are many 1 minutes, because if the calculation is less than 1 minute, then minimum requirement is 1 minute. That's why we kept it the same. And another one is a 100 liter per minute instrument. In each location, how many minutes you need to take a sample. Sampling procedure, how you will be achieving this goal. First, set up your particle counter with a 0 count check. In our Lighthouse Apex Z devices, we have a special button which describes all these 0 count before you start your sampling. This is excluded from your report, but still on your audit trail as a sample point and as a 0 count check. So every time when you first start, make your 0 count. Idea behind this to make sure that the particle counter is not sampling a background noise or any malfunction that you might find during the sampling procedure. Before you start, you make sure that the unit is running correctly. So to do this, each particle counter comes with a 0 count filter. Attach it to your particle counter, take the sample, and make sure that the results are given as 0. The sampling probe shall be positioned pointing into the airflow. If you are not pointing airflow directly, if it's a turbulent environment, the probe should be directed vertically upward. And you should make sure that you are selecting the right occupancy state and also make sure that you are establishing the right occupancy state requirements, and sample time and the volume of air to be defined. And then if there is an out of specification count is found at the location due to an identified abnormal occurrence, then that count can be discarded. But make sure, if you are going to discard, you should make sure that this is out of specification. This is not your limit exceeding. What does it mean? For example, you are taking a sample in at-rest conditions, but somebody break this rule and enter the room and make it operational. Then you can exclude this data. Or your isokinetic probe fell down, so you can abort this sample, and then you can say this is an out of specification. This doesn't mean that this is attributed as a technical failure of a clean room or an equipment or a poor cleaning whatsoever. Everything was fine. You take the sample, you are out of limit. This is not an out of specification. This is something you need to record. Your report will fail, and you should be make a cause analysis of this, identify it, take the remedial actions, and then retest the clean room. So this is how you will be performing clean room testing. There's one example for sterile manufacturing in the clean room. That's our design with HEPA filters on top. This is a production room. We are expecting it to be a rack system in pharmaceutical manufacturing. This clean room is giving us as a 6 meters by 9 meters, 54 meters square of a total area with 9 HEPA filters located. And there's a production area, the filling line after the deparinization panel on this part. The turntable is located here. And we have aseptic manipulation LAF unit also. The sterile room itself is given in different color, while the filling line is in the red, and aseptic connection LAF is a different color. So grade A for production, the filling line is in operation, and again grade A in operation for the aseptic manipulation location here, the LAF unit, and grade B, which is ISO class 7 in operation for the room itself. So 29 meters square of area, 12 and 3 meters square of area, we divide them. We removed the total area, 54, remove this and this area in order to make sure that we have enough sampling locations to be described for the room itself. First one was 10 locations because the 39 is larger than 36. So we moved into the next one, which is 52, up to 52 meters square of an area. We will be sampling 10 locations. 24, because we select 6 locations, because 10 up to 24, you should select 6 sample locations. And 3 meters square of area requires 2 locations to be sampled. How we will be positioning our sample locations? First of all, in order to position a sample location, we need to define our number of samples to be collected from table A1. Then we will be dividing whole clean room into equal area. I will describe this equal area expectation because in some cases you cannot make it. We don't expect you to measure every single point. Just try to make sure that each location is at least identical to each other. And depending on your risk expectation, you can also make a different structure for this. Select within each selection of sample location considered to be representative of the characteristic of each section. This is from the standard, but when you are reading it, please read it as a risk-based approach. Why I'm saying this? Because representative of the characteristics mean you should know what's going on in this clean zone. Within the zone, you should define all the risk aspects. And then you can select the right location. What if you select right in the middle of this zone? Nothing. If you are able to explain why you picked this location, then we are all fine with it. But if not, then you're just taking a sample from the center, still okay, but not a good practice. At each location, position the particle counter probe in the plane of the work activity or another specified point. So, in order to position the sample location, additional sample location may be selected for locations considered critical. Their numbers and positions shall also be agreed and specified. Additional sections and associated sampling locations may be included to facilitate subdivisions into equal locations. For non-unidirectional airflow clean rooms or clean zones, location may not be representative if they are located directly beneath non-diffused supply air sources, which means if you put your isokinetic probe right under the HEPA filter, that's not a good practice. Let's take a look at our clean room with this aspect. We need to select 10 locations and 12 locations for 6 locations for the production area and 2 locations for the aseptic processing. So this is where I'm going to locate, and I will explain why I picked all these locations for these 10 zones. First of all, I'm avoiding to place my isokinetic probe right under the HEPA filters within the zone. So I'll be very careful about not to place my particle counter isokinetic probe underneath these sample locations. Location number 1, I picked this point because all the materials and also operators are moving into the room through this door. And behind the door is always the highest risk possible location. And location number 2, I picked this in the close to the corner because I have a return air duct. Return air duct is giving me the highest possible counts. And if I am within the limit in this particular location, this means my zone is safe. This is a critical because operators are always moving around this machine, especially in this side of it during production. So I picked number 3 based on this information. Number 2 based on this return air expectation. Number 3, even if it is at rest or in operational condition, I'm picking up this point because I know that my operator is loading all the stoppers through this area. So it's a quite active area, and I want to make sure if it's an at rest, I want to make sure without having my operator's intervention into the area, room is quite clean. This location is quite clean. If it's an operational condition, I want to make sure that the operator is making the proper engineered strategy in order to introduce stoppers without giving additional particle burden into my clean room. Number 4, as you see here, it's nearby the operator's zone. My operator, through the RAP system, they're using gloves and moving around this, also this touch screen, they've been moving around. So I want to make sure that this location is giving the right limits. And number 5, that's quite homogeneous location. So I'm just picking the center of this point. In fact, I have a HEPA filter on top of my head, so I move it a little bit down. The next one, this location is where I have the semi-stoppered equipment to be loaded into my LAF, transfer LAF, in order to move it to the, maybe to the lyophilization station, or fully capped equipment will be moved from here to the other location. So this is a quite active area. So I picked this location. And location number 7, as you see, standard was expecting me to have an equal zones. Take a look at these zones. They are all fine, but my zone here is quite narrow because when you remove the machine itself, I only have this square and a little bit area here. That's why I said I am adding this location. I'm having a sample in this location because this is a quite active location for me. All the microbiological sampling activity around this is going through these glow ports. So I want to make sure that even this area is way smaller than the other locations. I have one sample location into this point. That's why if my structure, the size of a clean room, when I divide it into 10 locations, sample points, if I removed a critical points like this, while I'm overthinking about making the same size, exact same size locations, I don't prefer it. I just want to make my point. I said that's my critical point. I know the size is not equal to the rest. but still very important. That's why I'm going to sample it. And the next one, I just put right into the corner because I want to make sure that the air change per hour, the air circulation in this clean room is okay under any conditions given. And another location here, quite homogeneous area. That's why we're still thinking about the HEPA filters, but putting it right in the center of this zone. And the last one will be in the return air duct again. I know that this is one of the highest count possible because all the dust inside the clean room, all the particles end up in these sample locations. Two things that I want to say. One, when we say the return air, we're not expecting you to put these sensors right into the return air duct in front of the return air duct. Still, you will be in the production height. So what is production height inside the room? If my operators are moving around, it is like in the belly all the way to the head. Within between this area is the critical part for me to monitor. That's why I can suggest 1.2 meters from the surface. So this will be a nice point to be sampled. Number two, don't lie your particles in the floor and keep these isokinetic probe and your tubing in a spiral fashion. Don't do this. Put the particle counter on top of your cart, attach your isokinetic probe directly on top of your particle counter and take the sample. Within the room itself, it's a turbulent air, so you don't have to worry about this isokinetic sampling. So since it's a turbulent air, you can avoid using this isokinetic sample probe, still okay, but make sure you have this cart available during this sampling. But if you have to use this sampling tube, we will come later on, but make sure that it is short as possible, especially for the classification purpose. Next one is 12 meter square area. This 12 meter square area, we will take a look at the Annex 1 2020 expectation. It says sample locations should also consider all critical process zones such as point of fill or stopper ball. And this processing locations should be based on documented risk assessment and the knowledge of the process and operations to be performed in the area. And ISO says in 14644-1, ISO says representative to the characteristic of the section. So you will make your own definition between these two. So let's take a look at my sample locations, the online monitoring points that I'm using during this strategy. One, nearby the turntable, this accumulation table. Two is on the point of fill. Three is on the stoppering location. Four is for the semi-closed, semi-stopper products to be discharged from the machine to the lyophilization line. So I selected these four locations as my online monitoring points based on a risk assessment. So when I'm doing the classification for the same filling line, I need to sample 6 locations. This six locations, location number 1, I'll be picking the same location in order to make sure that the same risk assessment will be considered. Number 2, I'll be selecting this preparation area because before starting production, all the aseptic manipulations, all the needles, bulk transfers are made through this hedge. So I'm going to sample within this location. Number 3, I already have my sample point here, but I'm going to put my particle counter isoprobe right in front of the needles for at rest condition. The point for monitoring is next to the needles because I don't want my operator's hand with the gloves on top of the particle counter during production. But if I'm doing at rest, I can put that right in front of the needles. But if it's again in operation, I can move it into the same location. Number 4, I'll be using the same location for the stopper area. But number 5 is the new one, stopper ball loading location. I have a specific location for my classification here. And number 6, I'll be using the same location with my online strategy. Take a look at 4 out of 6 is based on my online monitoring risk assessment. Additional two is based on a knowledge. What is going on inside my clean room, especially in the production area? What will be the next two locations? Take a look at each zone. They're pretty much the same size. I don't worry. I don't care, because my idea is to make the sixth location smooth as possible, other than focusing on whether I'm taking 2.5 meters square area, 2.6, 2.7. I don't care. Most important part is to have these sample locations aligned to each other. And the online monitoring point for this aseptic manipulation location is here. And two sections. One will be directly to the same point. Two will be at the corner of the sample point. So data collection and reporting. We'll be moving into the next part. We'll be collecting data from these locations, number 1, 2, 3, 4, 5, and 6. And we will be preparing our report based on this information. This is the general summary. For ISO class, we are going to make ISO class N as an ISO class 5, which is grade A respectively. Occupancy state will be at rest for our testing. Target particle size for ISO 0.5 and 1 micron, which is 3520 and 832. Again, GMP requires 0.5 and 5 micron steel. If I were you, other than being certified for ISO or GMP, I would collect 0.5, 1, and 5 micron together. So one data set can serve for two. And even if I'm using for the ISO requirement, I will still watch this 5 microns. Number of sample locations based on table A1. This will be the 6 locations. And required sample volume, even the calculations are same. The flow is different because I'm going to divide this 20 to the largest particle size, 832 target, multiply by 1000 gives me roughly 24 liters, make it 25. And the GMP, 20 divided by 20 multiplied by 1000. This is where this 1 cubic meter of air to be sampled definition comes from. And room area is 12 meters square. My flow rate with the particle counter is 100 liter per minute. I'm going to use Lighthouse Apex Z series 100 liter per minute instrument. And single sample volume. In each location, I'm going to sample 1 minute because there is a minimum 1 minute rule. I'm not going to say, okay, every 15 seconds, I'm going to collect 25 liters, so make it 15 seconds. No, Annex B requires me to sample at least 1 minute, no matter what the flow rate is. So GMP, I'm going to collect 10 minutes of a sample in order to make sure that this area will be 10 minutes will be giving me a 1000 liter of a sample. So ISO 5 filling line, I have these locations 1 to 6. So expectation, you can take n number of samples. There is no limit from the standard. In fact, your protocol at the beginning should tell me how many samples you required from each location. So my expectation is to take at least 1 sample in each location and take an average of it, which is equal. But take a look at this location number 2. I have out of specification conditions. You can easily tell this from the data that I collect. So something happened. I have to take a note. I would say at-rest conditions have been deteriorated. Someone entered to the room, or my isokinetic probe fell down. This can be an out of specification. So I can disregard this information, discard this information, and take a second one and use it as an average. But don't play around this information, okay? You shouldn't say, I'm out of spec, but I will make this as an out of specification. This is unusual condition. Reason, if your location 2 fails, you should try to keep it up and running, but I'm sure the same conditions will find you in location 3, 4, 5, or 6 again. Because if there is a high concentration in one side of a clean room, since it's a turbulent air or the unidirectional in this example, it will eventually moved into the other locations, and you will start seeing the high counts in the neighbor areas, neighbor clean zones. So this test was passed. We'll be taking the second one for 0.5 micron. Before moving into this, take a look at this multiplexer. I just multiplied the average number of particles with 10 in order to find the 640. Reason I multiplied with 10 is because my particle counter is 100 liter per minute instrument, and my multiplier factor will be 10. If I was using 1 CFM unit, this will be 35.3. But this doesn't mean I should sample at least 1 minute, but instead I'm going to sample just 10 liters and multiply it with 100. No, that's not true. Or using a small handheld unit in a sterile area, instead of sampling 1 cubic meter of air for GMP, just sample a minute of data and try to multiply it with 353. That's not a good approach. Always go with the minimum sample required first. Then, in order to consider your limits based on the ISO classification, which is per meter cube, to be able to consider this, multiply it with this factor, then you will make a consideration between these two. And since the all locations pass for 0.5 micron, I'm okay with 0.5 micron. What about the 1 micron in ISO? As you can see, location number 5 is out of limit. So in this case, my customer's SOP says, I want you to take at least 2 samples in each location for 1 micron. I'm okay with it. I take 2 samples. An average, if you take a look at it, I'm out of spec for the location number 5. So the entire report failed for ISO. I will go back, make 0.5 and 1 micron together, take the sample, do this again. Let's move for the GMP 0.5 micron. I'll be taking 100 liters in each location. I take it, average is equal. There is a multiplexing factor, which is 1, because I already take 1000 liter. So I compared these 2 results. They're all fine with the 6 locations. What about the 5 micron? 5 micron, I take it another 1000 liters. You can do it at the same time, by the way, 0.5 and 5 micron at the same time, but just the report is separate. So I take the average. Since the average is equal to the original one, because I'm taking 1000, it's also equal to the meter cube of data. So I passed from this. So I am able to classify this clean room according to GMP, considering 0.5 and 5 micron. So the report part, we are coming to the end of our presentation. The test report will include your testing organization, name, address, and the date. What standard or regulation are you referring to? GMP, ISO 14644, or the specific report -1 2015? Physical location of a clean room or clean zone tested. Maybe all the adjacent areas to be defined. And you can also put the diagrammatic representation of sample locations from your clean room, like we did on the location table. The specified designation criteria for clean room or clean zone, including ISO class number at the beginning, the relevant occupancy state, considered particle sizes, test method you used, equipment certification, the current calibration certificates, and identification of the test instrument with the brand, name, number, make, and serial number. The test results, including particle counter data for the sampling locations, which means the thermal printouts or the raw data. The period for classification or reclassification in Annex 1 2020 draft, it is given as for grade A and B will be every 6 months, grade C and D will be 12 months. But if there is any change or unusual conditions in your clean room where your operational setting parameters for HVAC system was changed, then you need to do the reclassification. Interruption of air movement, which means you turn off your HVAC system for a certain period of time. When you rerun the clean room, you should run this test again with the performance qualification. Special maintenance which affects the operational installation, which means if you change the final filters, If you have new equipment in the room or the change of a design of entire clean room, this also requires reclassification. According to ISO 14644-1, demonstration of compliance will be at rest or operational classification may be performed periodically based upon risk assessment of the application, typically on an annual basis. Or ISO 14644-2 2015 version says the periodic classification will be based on a risk assessment, the extent of a monitoring system, whether if there is a monitoring system or not, and the data that are consistently in compliance with acceptable limits based on the trend and the level defined in the monitoring plan. So that's all for today as my presentation. We have a Q&A session now. I'll be checking out the questions part. That's always the toughest part because I'm having difficulties to see all these questions in one screen, but I will try to do my best. Okay, let's make it larger. Great. The minimum size threshold in an optical particle counter. Is there an advantage to over-specifying the minimum size threshold in an optical particle counter? Quite a technical question. If it's a calibration standpoint, the answer will be changed. But if you're just checking if we are considering, let's say, instead of 0.5 and 5 micron, taking 0.3 micron as a consideration, this doesn't make a huge change because the table given in ISO Annex 1, ISO Table 1, has its own specification for each particle sizes. I'm right in thinking that the definition, a properly calibrated particle counter with a minimum size. Okay, this is an explanation. 0.5 larger if it's the same efficiency and performance. No, actually not. The question is, if the particle counter is calibrated with a first channel of 0.3 micron, will it give the right results for 0.5 and 5 micron? No, technically, 21501-4 has a very extensive requirement other than the particle sizes. We have been testing 10 different parameters in order to calibrate our particle counters. So the smaller channel size is not really making a huge difference. And okay, since the flow volume is most airborne particle counters is controlled by a set of flow rate and a period in which the particle module is active, is the timing critical? Okay, most of the particle counters has a flow rate, measurement inside, especially for Lighthouse. We have the flow meters inside of each and every particle counter. So if it requires, let's say, 10 minutes to be sampled 100 liters, so if it is sucking this air within a short, or the pressure will be changing, then the result will also change in terms of seconds. This can give you 10 minutes, 2 seconds, 3 seconds. So it can change, but we are always making sure that the amount you require to be sampled is the fixed amount. Now the types of particles. Okay, so the question is, can we roughly know the types of particle contamination if there are high 0.5, 1, and 5 micron counts? In general, 5 microns, which you should expect having the HVAC system failure or operator failure, or operator failure means the gowning procedure is not okay, or the cleaning in general for clean room is failing. 0.5 micron is a nice indication of a proper cleaning, but you cannot specifically say what is the cause rate for these high counts. In fact, your microbiological data that you are sampling from your clean room will tell you whether if it is related to any specific contaminants in your clean room environment. Okay. For hand particle counter with 2.8 liter per minute, can I use it for classification? That's a good question. If you are trying to classify ISO class 7 and 8 clean room, I'm completely fine with it because your expectation is minimum 2 liters. For ISO, that's okay. But for GMP, forget about it. GMP, you should have a high flow rate instrument, at least 28.3 liter per minute instrument to be used for classification. And the handhelds, this 2.8 liter per minute instruments are quite inefficient for this kind of an applications. How often would you advise for a research laboratory and the biobank be addressed for containment for reclassification? Okay. For requalification, the classification period should be this kind of a critical application. The classification will be for particle counter purpose, the cabinets every 6 months, critical zones, even if it's grade B or ISO class 6, still 6 months. You can make it up to 12, depending on your trending. For example, if you take this 2 year in a row, if you have a set of 4 data, check this. If it is below from your highly less than the contamination you expect from your clean room, then you can move on. But if you are within the limits, barely, keep taking 6 months samples in this case. Is online particle monitoring required only for grade A and grade B during batch fill? Yes, grade A and B is required for online monitoring. Even today's section is just for classification. I can answer this question. Yes, grade A and B, not only with the batch fill, but before batch fill, preparation, changing all the equipments, getting it ready with the cleaning cycle, during production and after production for the certain time. In general, half an hour before and half an hour after with the production. This is what we call then online. Online doesn't mean 7/24, day and night, all the weekends. Online means before production, certain period of time, during production and after production, again, a certain time. Okay, another. Can we roughly estimate? We answered this part. I'm seeing one another ISTM. Okay. We talked about it. A couple of questions were about shall we keep sampling 0.5 and 5 micron for ISO? Yes. I do recommend. Even ISO requires 0.5 and 1 micron. They are all fine. Keep in mind, ISO is for all industries. It has been using in the electronics, semiconductor, aerospace, car paint shops. So they're all using it. And even one channel is okay for classification. Take a look at ISO class 1. There's only one channel size, which is 0.1 micron. So if you want to sample the entire area, then you are keep running up and running with the same size. For example, you can just use 0.5 micron to classify your clean room according to ISO. Reason we take 2 samples is because we want to keep it parallel for pharmaceutical applications between GMP and ISO. We try to keep it parallel. That's why we take 0.5 and 5 micron respectively, because GMP requires both. There is a limit for both in GMP. But for ISO, one channel size is okay for classification. But we are recommending you to take 0.5, 1 and 5 micron together. You can use this 3 data, not for ISO, not for GMP, but for yourself, in order to see what's going on in your clean room. I think that's an important point. If a portable particle counter has to be used in grade B, is it good practice to perform zero count in grade A? Then the purger for particle counters is damaged, not working. Not the best practice. We cannot expect. I recommend you to have these zero count filters, the spare parts you can order from your company, the supplier. Have these, because idea behind, you don't know if this LAF unit can provide this zero count all the time. Maybe there is a glitch on your LAF structure, or biosafety cabinet has a turbulent in it. we don't know. We don't want to add another parameter on top of our expectation. That's why having the original isokinetic HEPA filter on top of your particle counter is the best approach. If my product is manufactured under containment, okay, within the isolator, do we need to qualify the working space? Oh, for sure, yeah. No matter what, isolator, wraps technologies whatsoever, during production as a monitoring system, you have to classify it and you have to monitor it. Both in classification and monitoring, you should still make sure that you have the counts, not only for non-viable particles, also for the microbiological activity. Is rational required to be provided for each sample position selected during cleanroom certification? Yes, you have to have a list of your locations, at least a map of your strategy to point out where you sampled, and if you can put that into your SOP, why you are selecting this location is a best practice. But ISO is not requiring you to tell us why you picked this location. But best practice is to tell why you pick it. Reason, maybe in the long run, you are going to change this location and you will make sure that the risk at this point is not overlooked. And also, if the situation is changed, for example, if you pick this location because of a specific instrument nearby, but the equipment is not there anymore, then you will know from your records, or the other person will know that this condition is not valid anymore. So we came to the end. There are a couple of other questions that I can answer from your mail directly. Thank you very much for your time today, and hope to see you on our next webinar. Let's keep in touch. Thank you.